Hey, Miss Cindy. So this is my first milestone, and I decided I wanted to become a stenographer, all thanks to my mom. But I was also influenced by a TikToker, and her name is Jacqueline Randy. She is a diagnostic medical stenographer, and what interested me the most is that she's a travel stenographer. She currently works at Oklahoma Children's Hospital at OU Medicine and specializes in pediatric cardiography. This is just some of her background. Ideally, I want to work in Hawaii. Travel sonography to Hawaii pays drastically higher than a stationary sonographer, and I also want to go due to personal sentiments. Environmentally, Hawaii is beautiful, but it is humid, which is not great. And for job availability, it has high job security as they have numerous listings on Indeed. And to sum up my personal statement, I have only my mom to thank because she constantly brainstormed careers with me and found sonography. And after I get my bachelor's in biology here at UTSA, I will enroll in a sonography program to make all of this happen. So milestone 2 was the interview. The interview process made me a little nervous because I always want to be perceived in a positive light and intelligently. But as an interviewer, I can improve on my empathy and understanding towards others. I can be a little too critical at times, and that really needs to be corrected. I also think I need to improve more on feedback for the interviewee because I often went blank on what to say, whether it was positive or negative. As an interviewee, I can improve on stress. I need to stop overthinking because overthinking just makes things overcomplicated and it makes me more nervous, which will likely make me mess up. Milestone 3, this finally involves some math. So this is my function, and my scenario relates to obstetrics. So I go in depth of what each term of the function represents, but I don't have enough time to do that. So we want to know how fast the baby's heartbeat is increasing or decreasing at a particular time. So here, we took the derivative of the function, which is the rate of change of the heartbeat. And then here we plug in 4 into the function and we get 72, which is the number of heartbeats. If we plug in 2 to the derivative, we get 6.33, which is the rate is increasing in BPM. We found that there were no critical or inflection points, which means there are no points during the examination where the baby's heartbeat abruptly stops increasing or decreasing, and that the heartbeat will exhibit predictable behavior. Last, we graphed the original function and we get this, which matches my scenario of heartbeat progression over time. So for milestone 4, we did Riemann sums. I'm not sure if I'm saying that right, but this is our derivative. We graph it and we can relate it to the rate of change in blood pressure fluctuations in sonography. So here we make a table and we plug in the x values into the equation to get the f of x values. And using the f of x values, you can get the left-hand sum, which is 69.26 centimeters, which represents the change in blood pressure every 2 minutes, and it's an overestimate. And we get the right-hand sum of 42.4 centimeters, which is an underestimate. The average is 55.83 centimeters, which provides a balanced estimate of the total change in blood pressure rate. Lastly, using the correct C value with our derivative, you can see the left and right hand sums. So milestone 5 is the FTC, and it is the same blood flow scenario, table, equation, all that, as milestone 4. So next we need to solve the antiderivative, and this is what we get. And then we need to solve for the exact area, and we get 54.84 centimeters. To check my math, we put it through Desmos, and we get 54.84 again, which is similar to my milestone 4 average of 55.83. Therefore, we see that Riemann sums is simplified with assumptions, which can lead to inaccuracies in the actual blood pressure behavior. But FTC provides precise and exact measurements, and with the exact area, it provides more exact and reliable analysis of blood flow dynamics. We did it. We are on the last milestone, differential equations. So this is my function, and my scenario is that a sonographer gives a contrast agent at a rate of 75 milliliters per minute to enhance blood flow visualization. The rate it disperses is at a constant negative 0.3 with time in minutes, and we assume the patient has no initial contrast agent in their system. The sonographer wants to know the amount of the contrast agent that is in the patient's bloodstream after 1 minute. So to solve this, we use the differential equation, which gives us negative 0.3 y minus 250. And then we use the solution equation, which gives us 250 minus 250e to the negative 0.3 t. And with the t, we plug in 1 for our 1 minute, which gives us 65. So the contrast agent in the patient's bloodstream after 1 minute is 65 milliliters. So now we go to coding. Miss Cindy, you know I was on the struggle bus with this one. So let's just pray I got this right. So here we have the first graph, which shows a step size of 2. The second graph shows a step size of 4. And Euler's method was overall accurate, but more so in the first graph. So therefore, the first graph of h equals 2 gave better approximations. Based off the first graph, we see that the points plateau, and those constant points are our equilibrium, which we see is 250. This represents the inflow and outflow in equilibrium, resulting in a steady state concentration. So for my final reflection, this project made me become more open-minded in what I wanted to specialize in, whether it be general, cardiovascular, or obstetrics. I was pretty closed off to obstetrics in the beginning, but the third milestone was actually my favorite, which related to the baby's heart rate. And the interview process made me learn I need to be more understanding and speak more from the heart. Also, I never realized how calculus plays such a vital role in my field. But most importantly, I learned more about myself and my future goals. So that's it. We made it through the semester, and I hope you enjoyed my presentation.